Hello everyone, my name is Dr. Rebette Jones and today I'll be presenting IoT malware detection with GPT models. The proliferation of Internet of Things device had led to significant increase in cyber attack targeting devices. IoT vulnerability. Compared to traditional computing devices, IoT devices are more often less secure, making them attractive targets for malware attacks. Consequences: cyber attacks on IoT devices can have severe consequences, including theft of sensitive information, damage to infrastructure, or even harm. Detecting IoT malware poses challenges due to large number of devices and diverse range of malware types. Ineffectiveness of signature-based method, what we call traditional signature-based model, are ineffective for IoT malware detection as malware can be very easily evade detection by changing its signature. The rise of machine learning. As a result, machine learning-based methods are increasingly being employed by IoT malware detection. So generative pre-trained transformation or transformer, they call it GPT. Models are popular deep learning based method for IoT malware detection. Capability of GPT models, which is GPT models, are trained on massive amount of data or text data we call it, enable them to understand the complex relationship between the words and phrases. Ideal tool of IoT malware detection, what we say, is due to the ability to comprehend logistic nuance, okay, and GPT models as well suited for detecting malware. Okay, so let's talk about each data sets and challenge of GPT model, the effectiveness of changes, okay, the effectiveness of the changes of GPT model. So IoT 23 data set, what is it? The IoT 23 dataset, it compromised network traffic data for 23 different IoT devices, including cameras, or routers, and smart TVs, is used to evaluate the effectiveness of GPT models. What is the promising results? Well, GPT model trained on the IoT 23 dataset have shown promising results with the accuracy of 98.8% and a precision of 99.4% in detecting IoT malware. The Malware dataset was another dataset. Now, this Malware dataset contained a network traffic data from 10 different types of malware. It also utilizes the evaluate GPT model for malware detection. So the GPT model performance, let's talk about it for a minute. It's a GPT-2 model trained on Mavis data set, achieve an accuracy of at least 98.4% and a precision of 99.2% detecting malware. Let's address the challenges. So despite the effectiveness of GPT models, challenges such as interoperability and the need for a larger, a more diverse data set still need to be addressed. Okay. Okay, the machine learning based method for IoT learning detection. In recent years, there has been significant research on using machine learning, or you say ML, based model to detect IoT malware. Supervised learning, which means that one common approach in supervised learning where models are trained on labeled, benign, and malicious traffic data set. For example, design use a knee neural network to detect IoT malware using the UNSW NB15 dataset. The model achieved at least accuracy remarkably of 96.9%, demonstrating the effectiveness of supervised learning method by the IoT malware. Okay. So deep learning models such as CNN and the NSLSTMS are effective for IoT malware Detection due to the ability to capture, okay, complex patterning and network traffic data. Now, the study by Rubel highlights that successful application of deep learning method is detecting IoT malware, achieving at least 98.3%. By leveraging the IoT 23 database, which contains a diverse range of IoT devices, the researchers were able to demonstrate the generability of their deep learning approach. Okay? So, unsupervised learning method. Okay, so the unsupervised learning method of IoT malware detection. So, the unsupervised learning method offers an alternative approach to detect IoT malware without the need of label data. So, the study by Accu showcases the efficiency of clustering based model in identifying an IoT achieving impressive of 99.4% using the Miro dataset. Unsupervised learning is particularly valuable because it is in detecting unknown or zero-day attack, where label data may be limited or unavailable. Okay. We want to talk about transferring learning for IoT malware detection. So, transfer learning allows leveraging knowledge from pre-trained models or related tasks. It enables the efficient and effective detection of IoT malware. The Power study demonstrates the successful application of transfer learning, specifically using a pre-trained BERT model, the BART model, okay, for IoT malware detection, achieving at least 98.1% with the IoT 23 dataset. So transfer learning enables a adaptation to the model. Okay. So differentiating the factors of our work. Our work distinguishes itself from previous research for two key ways. One, using the GPT model. Firstly, we employed the generative pre-trained transformer. We call it a GPT, of course, model of the IoT malware detection. So you talked about now capability of GPT. GPT is a language model trained on extensive text data, enabling it to comprehend intricate word, phrase, relationship, making it an excellent tool for IoT malware detection. Okay? Now, evaluating, we're going to evaluate the GPT model on IoT 23 in the Maven set. Okay? So, we evaluate the effectiveness of GPT model on two distinct data sets. One was IoT 23 and then another one is a Mavis. The IoT dataset 23, I'm sorry, IoT 23 dataset. The IoT 23 dataset contains network traffic from 23 different types of devices. We talked about that. And then we had Mavis dataset. The Mavis dataset comprises network traffic data from 10 different types of malware. Okay. So the previous study on GPT, though limited research, has shown that effectiveness of GPT for security-related tasks like detecting phishing mails and spam messages. Okay. Phishing email detection. Wildlife exploit GPT to detect phishing emails and achieve an accuracy of 97.54%. Spam message detect. Kumar say you utilize GPT to detect spam message from accuracy of 99.28%. Building on previous study, our work extend these studies by exploring the efficiency of GPT for IoT malware detection. And the results are our study demonstrate that GPT model achieved an accuracy of 98.6% on a IoT 23 dataset and 99.3% on the Mavis dataset. Okay. Now, let's move on to the methodology overview. So code gadget extraction. Let's talk about that. So first we extract code from gadget from a network traffic data or IoT devices. Tokenization. The extracted code gadgets are tokenized using a tokenizer from a Hugging Face transformer library, converting them into neural token. Vectorization. The tokenized code gadgets are transferred into dense vectors that capture the semantic meanings. Okay, and then we have the GPT model input. The vectorized code gadget served as input to the GPT model for malware detection. All right. Now let's move over. We're going to move over to the GPT model processing training. Okay, let's see how we train. Okay, so now we look at the GPT model processing. The GPT model processes the vectorized input through multiple transformer layers to capture contextual relationship. Next, we have the fully connected layer. The output of the final transformer layer is fed into a fully connected layer, and binary classification determines the input indicates malware. 3, the training process. We employed the binary cross input, plus function, and atom optimization and trained for GPT model. Transfer learning. Transfer learning is used by fine-tuning a pre-trained GPT model on the IoT 23 Malware dataset. So, approaching the summary. Our methodology leverages code gadget, tokenization, vectorization, and GPT model is detected by IoT malware effectively by identifying patterns, anomalies, and code gadgets and capturing their contextual relationship. Our approach achieves high accuracy in malware detection. And the results showcase the effectiveness of approach on the IoT 23 and the Malware dataset. Okay. All right. In this section, we represent the results of experiment in IoT 23 and the Malware dataset using the GPT model for IoT malware detection. Our goal was to evaluate the effectiveness of GPT model in detecting IoT malware and assesses its performance on these datasets. So let's take a look at these datasets quickly. Okay. All right, so table 1 showcasing performance metric of GPT model on an IoT dataset. So this is table 1, this is metric, and this is the value, okay? Emphasize the accuracy, precision, recall, and F1 score value achieved by the GPT model on the IoT 23 dataset, okay? F score, recall, precision, and accuracy. As shown in Table 2, the GPT model achieved an accuracy of 99.3% on the Mavis dataset. Okay, the precision recall and F1 score were 99.2%, 99.5%, and 99.3% respectively. These results indicates that GPT model is highly effective in detecting IoT malware in the Mavis dataset. As part of our evaluation, we compared the performance of GPT model with other machine learning based methods used for IoT malware detection. So the objective was to determine if the GPT model outperformed these methods on the IoT 23 and Melvis dataset. Highlight superior performance of GPT model in terms of accuracy, precision, recall, and F1 score on both datasets. Okay, so one possible explanation for high performance for GPT model could be its ability to capture contextual information of the input data. The GPT model is trained on large amount of textual data and can learn underlying patterns and relationship between words and phrases in a given text. So in case of IoT malware detection, the GPT model can analyze textual description of IoT devices and their associated network traffic to identify patterns and anomalies and malware behavior. Another advantage of using GPT model for IoT malware detection is ability to handle various input length. Unlike traditional machine learning model, the GPT model can process input sequences of varied length without needing padding or truncation. Okay, so particularly useful for IoT devices for vary traffic pattern and network behavior. Okay. So our approach has several advantages over overall signature-based method. We know that it can detect previously unseen malware variants and identify patterns, anomalies, and code gadget indicated of malware behavior. The use of GPT language models enables our approach to capture the contextual relationship between these patterns, improving like malware detection accuracy. Future work can explore the integration of our approach into a real world IoT environment, including IoT devices security systems. Okay. Additionally, our approach can be extended to detect other device or other types of cybersecurity threats beyond malware, such as phishing attacks or network intrusion attack attempts. Thank you, and this concludes my presentation on IoT malware detection with GPT models.